here's where we left off last time. We left off with a fantastic example of common sub-expression elimination, and it was a fantastic example because it showed how badly our CSE does. It's just horrible. It doesn't do anything, actually. So you guys remember? We propagated I, so remember, this is CSE, common sub-expression elimination. Well, the goal is we have an expression like, for example, which expression? Well, it's very complicated, but this A times B here, and this A times B, sorry, this was my comment, this is why. Oh my god, okay, hold on a second. It's A plus B, and it's A plus B here, this would be, okay, but let's assume it was A plus B. This is a common sub-expression. We'd like to kind of be able to reuse the value that we computed here, down there. So what we compute in the CSE is which expressions are available in which variables. So here we know that the value of I contains the value of A plus B. And then we know that X contains the value of I times 4. And then we come down here, and what happens is this statement here covers everything with Y in it.
Okay.
And it adds that Y is I times 4. So up to here, we're doing really good. Up to here, we're in good shape. But then this statement totally kills us. Because this statement modifies I. As a result, we have to move everything that mentions I, either on the left or on the right, because the value of I changed. All the invariants, all the equations, all the things about I now have to be deleted. So we delete everything. We delete this information, this information, this information. We're left with nothing. We're left with the empty set. And then this empty set propagates down here, and then this intersection, everything becomes the empty set. Everything becomes the empty set. The empty set here doesn't even matter what we do here. We can go down this path, but the point is this intersection, right? CSE is a merged intersection, so intersection will completely cover everything. Now it turns out that this path is not any better because we kill the information about I as well here, so we lose pretty much everything. Yes? Does everybody see how bad it is? So, what would we like to be able to do here? So you, as a human being, can look at this program and see the opportunities. What opportunities do you see? Yes?
Sum of P plus B.
What?
Sum of P plus B.
Yes, well, okay, so first off, this is screwing us over here, but let's assume that we have an ordering, and I think that we have the A plus B here. So we want to keep A plus B. So it seems like, dude, you've computed A plus B, you should somehow be able to use it there. If we're only storing a different variable name there, or something else, then we'd be able to use it. Okay, if only it was renamed. I wonder what will do that for us, but okay. Okay, what else?
Times 4.
Times 4. What about times 4?
All three
Isn't
spots.
that a more ratio?
What?
All three spots are going to do it times 4.
What?
Right, they're all doing A plus B.
Are they?
X equals X top is.
Wait, what?
Yeah, A
So
plus
use
B.
J times 4, which is storing the old I, and Y is I times 4 already.
Yeah, N
And
is
then
A
on the
plus
bottom,
B.
W equals 4 times N, which is.
Right.
Yep.
Well, this is like I. This is really I times 4. But it's not. It's kind of confusing because, I mean, it really is the same value that was computed here. It's the same thing here. That we put J in here, but then when we cover I, and then, so do you guys see how it's the same thing?
Mm-hmm.
But somehow we're not able to see that. And what about this thing here?
That's also I times 4.
Yeah, so if we kind of move this around, these multiplications the other way around, we have n times 4, then it's actually really the same thing, right? Now, our analysis is not able to see any of this stuff. And part of the problem here, so if we kind of just take a step back, part of the problem here is that available expression is overly sensitive to the name choices, right? The variables have been named slightly differently. We might have been able to do a better thing. And we're basically also sensitive to basically assignments like copy propagation, right? Because we didn't see the copy propagation. So one of the things that will help us here is to use SSA. So that's the first thing. The SSA will rename everything for us. We'll create every single assignment. We'll get a unique kind of variable that it's assigned to. And the other thing that will help us is if we do copy propagation before doing available expressions, that will also help us. As we'll see with that example, the reason why you're not seeing this thing here is because you like to do copy propagation. And of course, if you did copy propagation here, you wouldn't be able to do any copy propagation because this I cannot be propagated here. You can't just say I times 4 because this I is being assigned here. But with SSA, all of these will be different I's, so we'll actually get the flexibility to do all this stuff. And then the other thing is that we can actually run things over and over again. So let's take a look at what this. Oh wait, hold on. Whoa. Before we move on, so we got to do everything SSA. But now what are our flow functions going to be like for SSA? So remember, we actually did this last time. Wasn't this like the coolest moment ever? This was our flow function originally. It had all of this mess. We figured out that we can delete everything when we're in SSA. Sorry, we can remove all of this stuff in the flow function and only keep this when we're in SSA. Because the reason why we did this was because here we are assigning X, so we want to basically delete all the facts that involve X. But basically, if this is the only assignment to X, there can't be any previous facts about X, so we can just not have this. And here, our big worry was that somehow, what if Y is the same variable as X? But here it can't be that way because this is the only assignment, and actually you can't reference. This will be the defining assignment for this thing. There's no way that this can reference itself. In fact, the only way it can reference itself is actually if somehow there's a fine node and there's a loop. So we can actually delete all those things. Does that make sense? Everybody sees? So it makes the flow function a lot easier for assignments, but on the other hand, we do need to be a little bit more careful about fine nodes. Why do we need to be more careful? So we need to, actually, first of all, we need to handle fine nodes. We need to have a flow function for fine nodes. Now, the fine nodes have, in some sense, two edges coming in, and the simplest thing you can do is just intersection. But if we do intersection, that may not be the best information. Right? Because think about it this way: if you have two things coming on either side, right? You'll have like a phi node like this, like x5 is equal to phi of, like say x1 and x2 or something like that. And if let's say on this side you have x1 is mapped to something, some expression e, and on this side you have x2 is mapped to that same expression e. You do the intersection of these two things, what do you get? Empty set, because x1 and x2 are different variables now. So you could do the intersection, but actually if you do the intersection, you will lose everything. Because basically, all the information on these two sides will be about different variables, very likely different variables. So you're actually going to lose a lot. So what can we do instead? Does anybody have any ideas?
Fresh out.
X5 points to all values E such that X1 and X2 both point to E.
Right, so wait, so X points, well, we call them Y and Z here. So if X points to E, such that what?
Y points to E.
So sorry, Y has the value E in 0, which is the one coming here, and Z contains the value E on the other one. Right, so we're allowing for different variables, because basically there's two, it's going to take Y when you're coming from here, and it's going to take Z when you're coming from here. So basically the point is that both X, Y, and Z, have the variable E on the two sides, and you can basically just maintain that information. Cool beans. So now we go back to our example, and we can actually do it. And notice that this example is, so we just reorder. So first of all, we use the canonical ordering for the thing. So basically we put A first and A first there, so the ordering on the front is the same. And we also do the multiplication. We put the constant on the right, so we kind of have it in kind of a more kind of uniform way. So now this is SSA. Wait, what happened? Oh, fine. I'll just show you the answer. Yeah. It's not that complicated. But really what happens is you have, so you put this all in SSA form, and the way it works is you relabel, so this is I1, X1, you put Y1, you basically give a index, you give a subscript to every single one of these things. And then here you need to insert a phi node for I. So I comes from either I1 or it comes from the one in the loop, which is I3, right? And then this I4 here is used here, so that's the value that comes from the loop and it's used there. And then what happens? Well, then what else we did is that once all these are given different names, this was a J, right? So actually notice how previously, in the previous slide, that was a J. Originally this was a J, so this would be like J1 and this would be J1, right? But now notice how, because if you put this being J1 and this is J1 and this is, let's say I2, because that's I1 and that's I2, then you can replace this, oh no, wait.
I1.
I can now replace this with I1, and notice how copy propagation works perfectly now. I can just replace it because this is I2 now. It's not I anymore. It doesn't conflict. So now I can replace this with I1, and that's exactly what this thing does. Right? So this is why this is I1 here. Okay, does everybody follow what happened here? We just convert the SSA into copy propagation. Any question on this? So now, this is so cool. I mean, everything has its own name. So this M1, you can immediately see it's the same as an I1. And I1 will never be modified again, right? So I could just like, it's almost immediate. I mean, that I1 will get propagated all the way through, so I could just take this and say, well, this is I1, right? Are we done now? What do we do
No,
now?
and then you have M1 is I times.
Okay, what do we do there?
Can't get into I1.
W1
Copy
equals
propagation
I.
again. So notice how we did CSE, and now actually we did copy propagation
SSA.
to get this, and now we're doing, actually this one again. Oh wait, hold on. We can just use X1 here. I forgot, that was obviously another one, right? We can use X1 here. But now if we do another round of copy propagation, this will go here and become I1, and now we can do CSE again, and we'll get X1 here, right? So the point is, you can see how copy propagation and common substructure elimination kind of work, enable each other, right? Basically, copy propagation, this copy propagation here enables CSE, and CSE, which replaced CSE, made this be I1. So CSE enabled copy, it enabled this copy propagation, right? There was no copy propagation to do here. But by running CSE first, that exposed opportunity for doing more copy propagation. Does everybody see that? So there's this mutual dependence. And here, this is an example where copy prop enables CSE, because before doing the copy prop, this was J1 times 4, we wouldn't see that thing. So copy prop enables CSE, and then here, CSE enables more copy prop. And that's why a lot of times you actually want to run them one after another, and you want to kind of iterate until you reach a fixed point. Got it? Got it. Okay. But the message here is also that SSA made it a lot easier, right? SSA was a big enabler with this stuff, because it allows us to do copy propagation. and allowed us to see this common thread expression, even though I was completely reassigned, everything happened, that I1 remained there. Okay? Okay. So pointer makes things more complicated. You know, I mean, there's many ways to do this. The simplest way is to basically use this, basically, which is that basically you have variables where you have certain variables that nobody points to. And Java has that, for example, and locals in LLVM are like that too. I mean, essentially, they're actually, you can build SSA on top of that. And Java is like that too, right? In Java, your locals can't be pointed to. Actually, even globally, any variable can't be pointed to. It's just fields that could be modified. But variables, they can't be pointed to in Java. So, okay, so SSA helps with CSE, but let's see what else SSA can help us with. And to see that, we're going to talk about loop invariant code motion. So we haven't talked about loop invariant code motion, and also we're kind of going to first talk about the setup of what loop invariant code motion is, what loop invariance means, and then we're going to do loop invariant code motion without SSA, and then we're going to see how SSA just makes life so much more beautiful and worth it. This makes it much better. So let's talk about loop invariance. So the way it works is there's two parts to loop invariant code motion. The first is figuring out, it's actually very similar to a lot of stuff. You first do an analysis, then you do a transformation. The analysis figures out what things are invariant, and then the second step is to actually move those things that are invariant outside of the loop. Either before, which is called code hoisting, or after the loop, called code syncing. So let's take a look at an example. So the idea of loop invariance is that every time around the loop, there are certain computations that you compute every time around the loop, and they will, despite you computing them every time around the loop, they will always compute the same exact value. Every time you go around the loop, that expression will have the same exact value. Okay? And that's what loop invariant, if that's the case, that's a loop invariant computation. Here's an example. Let's take a look at this example. What is loop invariant here? There's a loop. So what are loop invariant computations in this loop? What?
Q.
Two?
Q.
Q? Q. For sure. Yes. So because y, so this y, well, I mean, in some sense, this y times y is loop invariant. It computes every time you run it, it computes the same thing. Cool. Okay. What else? So this one's loop invariant. What else is loop invariant?
I guess the Y.
Which one?
The Y value, not a statement. Are we talking about statements or variables?
Expressions or statements. I don't know whichever one. I mean, this expression y times y is loop invariant. This q is also, well, this expression now, this q, I don't know if it's loop invariant or not, but what about this thing? Is this loop invariant?
Yes.
Okay, that one's loop invariant. So that expression is loop invariant. What about this one? What?
If we're using SSA, that should be a loop invariant.
No, let's not use SSA for now.
It still is. If you execute it, it's always going to have that expression is always the same. The resulting W afterwards is not, but that expression W plus 5 would be.
So you are claiming that this W plus 5 is always, this W plus 5 always computes the same thing.
Not that it'll always be.
Right, but if it's computed, it does compute. So this W plus 5 is in fact loop invariant. Now the value of W after here is not loop invariant because it'll change on loop iteration. So in fact, this W plus Y is not loop invariant. This is not loop invariant because Y is loop invariant, but W is not. What about this? Nope. Yes. What?
No.
No.
The X changes every time around. The X plus Y is always going to be, I mean, X plus 1 is always going to be a different value.
I see, so X gets incremented around the loop every time, that's your claim, so X gets incremented, okay. And the same thing with this one, right? This Q gets incremented every time the loop, so.
No. Q plus
No?
Q plus 1 there is already being leased out by Y times Y above.
Oh. That's a tricky example, huh? Well, you guys thought through it. Awesome. So, okay. Yeah, I mean, this looks the same as this one, but it's not, because this Q is being assigned here, which is Y times Y, and that's invariant. So this plus 1 is also going to be loop invariant. So we do have this being loop invariant.
Isn't it actually dead code, all that?
What?
Isn't it actually dead code or redundant code rather than,
Wait, now Q gets Q plus 1?
yeah, no,
Because Q is going to be thrown out.
Let me assume that there's a code after this loop that uses all the variables. So it uses that, so that makes all the variables live on every single loop. Yeah, I'm not sure. This is just a snippet, and there's code afterwards. So okay, so that's what we want to figure out. So the way we can detect loop invariance is that we can kind of do this recursive analysis where we, I mean, if you kind of think about the definition, right? So constants are loop invariant because it's every time. I mean, it's the same value every time, and it's a variable, and all of the definitions for that variable are outside of the loop. So if you have a variable and it's defined only outside of the loop, then obviously it's loop invariant because it's only defined outside of the loop, so the value gets outside of the loop, and that's it. And then there's kind of this inductive case where if it's a pure computation whose argument is loop invariant, then that expression is also loop invariant. And pure here means that there's no side effects, there's no bizarre things going on. It has to be a computation where every time you pass in, you know, the two arguments, they actually will, the result of that computation will be fully determined by the values of the input. So an example of a non-pure, I mean, for example, a random number generator is not, like, you know, even if you pass in a loop invariant thing into a random number generator, it's not going to produce the same thing every time, right? So this is, it has to be a computation that kind of, it's a, parameters are always the same, you always get the same answer back. And basically, if it's a variable, basically with one reaching definition, and the right-hand side of that definition is loop invariant. So if you have a variable, and you know that variable is being assigned here some loop invariant computation, then this X is also a loop invariant. Now the reason why you only want one reaching definition is because if you have, for example, this situation where you have a branch inside the loop, and X is set to a loop invariant thing on one side, X is set to a loop invariant thing on the other side, but the branch kind of, you don't know which way it goes, then you have more than one reaching definition, and then you can't say that this X is loop invariant, right? Does that make sense? If you have loop invariant on this side, loop invariant on that side, it basically, it has to be only one, there only has to be one reaching definition. And this W example is a perfect example of this, because this is loop invariant, but this W is not, because there's multiple reaching definitions for this W, right? There's this one, and there's kind of the actually, there's this one too. Actually, that thing's broken.
Why?
Huh?
Why is it broken?
Oh no, I just want to slow on. Oh no, it's not broken. Yeah, sure. Sorry. It's not broken. It works, yeah, no. It's not broken. It works perfectly with that. Because there are two reaching definitions, this W is not loop invariant. The only way it would be loop invariant is there's only one reaching definition that's loop invariant, then it would be. And it shows that that's important. Okay? Perfect. Okay. So, computing that, I mean, basically the simplest way to do this, you can actually build an iterative data flow analysis if you want, but it's actually pretty complicated to do that. The simplest way to do it is to build a depth use chain and actually to kind of inductively kind of start off with base cases and kind of inductively grow your set of loop invariants that way using the depth use chain. And basically there's another option to do the same thing, but you basically use SSA instead of just regular depth use chain. So let's first build it using depth use chain. So here's the thing on the right. This is our cheat sheet on the right. It tells us what the rules are. And this is our control flow graph on the left. And we don't have depth use chains yet, but now we do. I drew them very, very quickly. So these are the depth use changes. Wow. It's very colorful, huh? They're all so different colors for the different depth use chains. But you can see how it's going on, right? This Q like goes up here, and this X has two reaching definitions. One, actually wait. Yeah, this X has one from outside there, and one from inside the loop. Right? This X can come from two different places, either from outside the loop or from this compartment. And then W comes from here. This W comes from there. This Y is a kind of a mess. All these Y's can come from those two things, and this Y also can come from those two things. Cool. So now what do we do? Now we use the thing on the right, and we just keep on going, and we just keep on adding more things. So all these constants are loop. This expression here, this 2, is loop invariant. This 5 is loop invariant. What else? This 1 is loop invariant. This 1 is loop invariant. Okay, well that's pretty easy. And what about? It's a variable use. All whose definitions are outside of L. So what is that? Who would that be? Huh? Y. The Y. The what?
The expression Q equals like
Well, I'm not there yet. I'm just here. I'm not at expression yet. I'm just at individual variables. So first, let me just check mark this one. So that one's loop invariant. That one's loop invariant. That one's loop invariant. That one's loop invariant. And then, so we're only looking at things in the loop. These are outside of the loop, and this Y has definitions, but they're all outside of the loop. So all these Y's here are loop invariant. Okay, so all these uses of Y are loop invariant. Cool. And now we can apply our rule here. So if we have a pure computation, so all these computations are pure, like plus and multiply. I mean, they're given arguments, if the argument's the plus, if you call plus multiple times and the arguments are the same, you'll always get the same value out, right? So where can we see a pure computation that has, so here, right, this Y times Y, both Y's are loop invariant, so the expression is loop invariant. So this expression here is loop invariant. Okay, what else? What? Oh, this one, yeah. Cool. What else? Nothing else, right?
W plus 5.
What?
Oh no, not yet.
Not yet. Not yet. We'll get there, but not yet. So far, if we just apply this rule, that's it. That's what we have so far. But now we have this. So it's a variable use with only one reaching definition, and the right-hand side of the definition is loop invariant. So this W falls into that category because it has only one reaching definition, and the right-hand side of that definition has been labeled as loop invariant. Aha! We do this, and now our first rule kicks in. This rule can rest. So basically this 2, so these two become this. And then, oh wait, this one. So this Q as well. This Q has only one reaching definition, and the right-hand side is loop invariant, right? Because I labeled with this arrow, that's loop invariant. So that Q is also loop invariant. And now we have this plus, which takes two loop invariant things, and so this is also loop invariant. Notice how we don't label this W as loop invariant because it has two reaching definitions. And even though both reaching definitions are loop invariant on the right-hand side, this W itself is not loop invariant because we don't know which one we're getting. Each time we're on a loop, we may be getting a different one. And that's it. If you try to apply these rules more, that's it. We can't apply them anymore. Isn't that cool? That's pretty cool. We just went through all these rules, did a thing, iterated, as we always do. We iterate, and now that's it. This is all the things we can figure out. And thankfully, it's exactly what we had kind of intuitively written down as being loop invariant, right? So it's nice. So the algorithm kind of figures out what our intuition was from before. Any questions on this? Okay. So if you use SSA, SSA is not going to really simplify things too much in this case. It'll actually be useful for the code motion part, but still, let's see what happens with SSA. So basically, the rules remain the same. It's just that if you look at it, basically, every time you have something, there's always going to be only one reaching definition, right? So remember here we have this thing where we said, oh, with only one reaching definition, we don't need to branch, like check if it's one reaching definition or more than one reaching definition, because whenever you have a variable in SSA, if you call the def use chain, there's only one reaching definition, because there's only one assignment to that variable, like they ever have in the program. So basically it's like here, it's not all of whose defs are outside. There's only one single def for that thing. So basically now you don't have multiple things to check. There's just one thing to check. So now what I did here is I wrote down the rules on the right for SSA-based loop induction loop invariance, and here I inserted the phi nodes. Oh, and one more thing actually before we go there. So phi nodes are not pure, right? So you can't. The problem is, a phi node, it's used for merging. So the phi node represents information that could come from different parts of a branch. And so even if both things coming into a phi node are loop invariant, the phi node itself, expression, is not necessarily loop invariant because it's going to decide which one of those two things it'll come in. It really represents exactly this W, right? That basically this W here will have two things. So there'll be a phi node here for W coming from here, W coming from there, and basically that phi node, once you combine the two, that phi node is not going to be loop invariant, even though both parameters are loop invariant. So phi nodes are not loop invariant. So here we've inserted the phi node. Notice there's this phi node here for W, and now we can basically follow all the stuff. So let's see. So certainly, okay, so the phi nodes are not loop invariant, so we said that already. And this is not loop invariant. Okay. So now here we look at this x2. Well, x2 comes from the phi, and that's not loop invariant, okay? So the y3 comes from here, up here, and that's not loop invariant. Okay, this is not loop invariant, so this is also not loop invariant. The y3 again not loop invariant. Okay, w1, where does that come from? Oh, it comes from right here, right? But that's not loop invariant either, so it's not loop invariant. This w3, well, that's definitely not loop invariant. Now this x2, where does this x2 come from? It comes from here. So that's not loop invariant. It comes from a phi node, so that's not loop invariant either. We're doing really well here. This is very fast. Okay, Q, what about Q? Well, Q comes from Q1, and Q1 comes from here, and that's not loop invariant either. Okay, fantastic. So we've made this really simpler, but it's also really bad. So what happened? This nastiness. Nastiness has ensued. Yes?
So basically the phi nodes don't allow for any reaching definition outside of it. And that's why we have this problem.
Phi nodes don't allow for, so yeah, I mean, So let's, yeah, right, well, okay, so let's,
Definition in the loop.
right, well, let's take a look. So what was the key, so where does the badness start? So the badness started with Y. So X was not loop invariant before, so that's fine. But this Y, previously, remember Y, so if you look at the previous example, we were able to figure out, so Y comes from, right, so Y has two reaching definitions, and they're both outside of the loop, and so we labeled Y as loop invariant, and then we were able to figure out a lot of things based on that Y. But now we are not able to do it because we have this fun node here at the beginning of our loop. And that is a shame. Don't worry though, we'll fix it. I know you guys are worried. You guys are like, oh no, what's going to happen? It'll all end well. We just have to find what to do. So, why do we have a phi node? So, why do we have a phi node for Y? There's something weird about this phi node for Y. What's weird about it?
Y3 is input.
What?
Y3 is the input to something.
What's that?
Y3 is the input to the final.
Yeah, so it's kind of like there's three inputs. It's kind of weird because, well, because there's three reaching definitions. There's a Y from here, Y from there, and then Y from back down here. So how else could I, so, okay, what could I do? How else, so, yeah. How else would I be able to write this phi node for Y?
Should be possible to remove Y3 at least, because it's always going to be Y1 or Y2.
What you said is it's totally on the right track, but it's technically incorrect. You actually do need a Y3. And you said so you said, oh, but Y3 is only Y1 and Y2, or Y2. So actually you do need a Y3 because,
And you have to remove Y3 from the list of Y3.
aha, so what you want is you want this to be this phi of Y1 and Y2, right? In some sense. And that's indeed what you want, and in some sense, but what's actually happening is that really it's actually, you don't want, but there's still a problem, even if you just did that, doesn't quite solve the problem. Part of the issue here is that this phi node for X should run every time we're on a loop. But this phi node for Y is only meant to merge Y1 and Y2 before the loop executes. Right? You don't need to run this phi node every time around the loop. So in fact, the way to actually do this is like this. Because Y1 and Y2 are being defined in the branch before the loop, and then you want to merge them before you get into the loop once, and then you use Y3 everywhere else. This phi node for X really has to stay in the loop because you're actually redefining X inside the loop. Okay?
So that the use chain only points external to the loop for yourself.
Yeah, I mean, actually, the way you would do that is you would actually when you build your control flow graph, you would add this special node, which is called.
You have to know that you can do that.
What?
That you're allowed to pull that out.
No. So you create a special node. It's called a loop free header. So actually, the thing that was weird about this thing is that I had a node with 3 input edges. So what you can do is you can do this thing called a loop free header, and you actually put this, or some people call it a landing pad. I don't know, I'll tell you why in a second, but, so it's a pre-header in the sense that it's basically, it's a block which you can use to put things, to move things out of the loop. So when you have to move something out of the loop, you want to have this landing pad where if you throw stuff from out of the loop, you want them to land in a nice spot. And you need, so this is usually something that you do ahead of time when you actually have any loop. If it doesn't have a special block before it, you kind of introduce it, right? Because if we actually think about this thing here, if we wanted to add if we wanted to make a computation and move it outside of the loop, where would we put it? There's no place to put it, right? Because if you put it here, it's inside the loop. If you put it here, it's only on one spot, it's conditional. So what this thing does is it creates this loop pre-header, and then if you introduce this empty block here, then SSA conversion will actually insert the final in the right place. I mean, because it's just, there's no point in inserting it here, because it's here, this is the merge, you want to insert them as early as you can. This is the merge, this is the merge place where both Y2 and Y1 are live, and you can merge them. So, okay, and now, if you do it here, everything works out. Super awesome. Right, so this is not loop invariant. This is not loop invariant because X2 is not loop invariant. This is loop invariant because Y3, there's only one Y, right, this Y3 is from outside of the loop. So this Y3 is loop invariant, that Y3 is loop invariant, this is loop invariant. This is loop invariant too. This phi node is not loop invariant. So W1 is loop invariant, so this is loop invariant. And then W3, this is not loop invariant. X2 comes from the phi node up there, it's not loop invariant. And Q2 comes from Q1, and that is loop invariant. So now that we've adjusted a phi node to be in the right place, we run our algorithm, and it's very simple. There's much less, it's basically much kind of more direct. Okay? Does that make sense? So we kind of recovered our algorithm. It's good news. Any questions? Yes.
Does it still make sense if the initial assignment of X1 and Y2 are switched?
Wait, the initial assignment of here?
Yeah.
What do you mean?
X1 and Y2, like they're switched.
Oh, so I put Y2 up there and X1 here? Yeah, it's the same thing. Yeah, because Y2, I mean, the point is this will still be loop invariant. I mean, this Y3 is outside of the loop. Once you start executing this loop, this Y3 doesn't change anymore. Yes?
So how did we know the correct phi node to pull out of there? I mean, we have 3 phi nodes, we only decided to pull out one by observing that.
Oh no, we didn't pull it out. We didn't pull it because of loop invariant code motion at all. It was just from, I mean, so insertion of phi nodes is so there's a lot of research. People have done a lot of different things. It's non-trivial. There's well-known algorithms that you can just look up and you just literally will tell you if they use dominance frontiers, they use all kinds of things. You just re-implement it and it works magically. But people have looked. It's a nice theoretical topic. People have actually investigated this. But the point is, you know, certainly at this merge node, both Y1 and Y2 are live, and so, you know, and Y is used later on. So we know it's, sorry. So both Y1 and Y2 are live, and Y is live in general. There'll be a Y later on. So it doesn't really make sense to put the phi node up here. You want to put the phi nodes closer to the, you don't want to delay phi nodes. You want to basically put them in as close to the place where you need them as where the things get merged as possible, right? So yeah.
Could you make, would a rule like saying something like if everything in the phi node is a loop invariant, with the exception of like a self-reference, that you could pull it out? Like here, why?
We're not pulling anything out. Hold on.
In terms of if we're allowed to do,
Wait, you mean labeling loop invariant? You mean?
How would we know that we can pull that up? Like how? What is there?
Wait, hold on. Let me just clarify here. We are not. So far, that putting that phi node here versus up there is actually just an SSA conversion issue. We have not yet talked about pulling any loop invariant computations out. right? I mean,
Right.
we're just identifying them, we haven't even talked about what.
Prior to loop invariance then, why were we allowed to pull the Y out and not the X? I mean, I can reason about why you can't pull out the X, but there has to be some rule that says we have to be able to code that somehow, right?
Right, I mean, well, the point is, if you have this empty block here, suppose you do, if there's nothing in it, at this point, at the beginning, basically you can look at every merge point, every merge node, you look at, are there multiple reaching definitions for a given variable at this point that are live, and if so, insert a merge node. So I'm going to insert, and I'm going to do this as early as possible. So here I'm going to insert something for Y, but not for X, because X is only one reaching definition for X.
So the idea was you didn't actually pull it out of the later block, we would have created it in the first place.
Exactly. In some sense, you would have this as a loop header or landing pad inserted there already for you to insert things, and you would insert this thing here because there's Y1 and Y2 are both live, and there's a merge node, so you insert a phi node. Here, there's no phi node for X because there's only one X. So there is a merge node, but there's only one reach definition for X. There's no need to put a phi node. Here, there's a merge point, and here, once you've inserted this phi node, there's only one reaching definition of Y. So there's no need to insert a phi node for Y. But there is a need to insert a phi node for X because I have an X coming from there and an X coming from inside the loop. So that's why I need a phi node for X then. Okay. So now, let's talk, so that was loop invariant computation, figuring out what things are loop invariant. So the next step is actually figuring out what we can move. So, say we found a invariant computation when we want to move it. When is it legal? So the key is that we want to preserve the relative order of invariant. So first, you want to preserve the relative order of invariant computations. To basically preserve the data flow among those invariant statements. So for example, if there's multiple loop invariant computations, they all depend on each other. When you move them out, you want to move them out in synchrony, right? So you don't reorder them when you move them out. And in fact, it can get a little bit complicated with things like this. Because, so actually, for example, if I want to move this thing out and this thing out, that's fine. But if I want to also move this thing out of the loop, and I want to move them all up there, I need to maintain this dependency, right? So I need to make sure I execute this first and then this, because this one depends on the other one, right? So I need to make sure when I move them out, I keep those dependencies right. Now, so this, can I move that one out? This one?
Yes.
Because the phi node in the next block will just leave it and it's still not like.
Right, so I can move this computation out, this W2 out as well. But then again, I would have to be careful to move it in a way that this W1 gets assigned first, so I maintain this kind of relationship, right? So there's these kind of dependencies that I have to maintain. So that's the first thing, is maintaining the dependencies among all these loop invariant computations that you're moving out. If you're moving out one thing, you got to keep all of those invariant, all those dependencies, right? And you also need to preserve the relationship between invariant computations and other computations inside of your loop, okay? And this is where it actually gets a little bit tricky. So here's an example. We're going to start with an example that's not an SSA form. So this is not going to use SSA. It's going to just use traditional kind of just normal, you know, basically like we did before SSA. Okay. So here's this example. So this is a branch on this condition, which is a conjunction of these two things, and this is the true side, that's the false side, and that's the loop. So, okay. So let's first talk about what is loop invariant in this loop. What's loop invariant? Okay. What else? A and B. So this whole expression is loop invariant. What about here? So this Z is loop invariant, but the X is loop invariant too. So this whole thing is loop invariant too, right? Right, I mean, both these A's are coming out from out there, they're not reassigned. This is loop invariant, so this is loop invariant, so this, and this is from outside loop invariant. So these two statements always produce the same thing. The only thing that's not loop invariant is I, which gets incremented. Awesome! Let's move them out of the loop. I propose we take these two statements and we hoist them into loop invariant. What could go wrong, right? I mean, I'm going to hoist them outside of the loop. I'm going to run them once, right there. Again? Uh-oh. Divide by 0.
You have to see the value of 0 as participant. If you hoist above that, then you might be divided by 0.
So you're worried about this thing. If I move this out of the loop, if there was a guard here that made sure that I never divided by 0, but then when you move it out of the loop, division by 0 might ensue. Okay, that's bad. Okay, fine. So let's not move this one out. That one's going to cause a... Does everybody see the problem there? Okay. Okay, fine. So let's move this one out. Then at least we should be able to move that one, right? No?
What if, oh wait.
Yeah, we can? No?
You could verify that I is basically the only reason you couldn't is if you're never going to execute it, because we know that we will. Oh no, not execute 0. So then you still could.
So can I do it or not? So let's say,
If do 0, you would never change X, and then you want to get 1. Right?
We'll get it on result.
right, so what's the problem here? It's this thing here, right? So, I mean, basically, yeah, I mean, this X here, I mean, we don't know, so actually, it's confusing, right? I mean, but the thing is, if I move, so, wait, is it okay or not? It's kind of confusing.
In one case, if Z is not 0, you'll end up with X equal to A plus B, then Q.
Right. So the problem here is I have this X here, and I'm going to move this assignment here, and this, I'm changing the dependency. This X basically now will never be able to come from 0. Previously, it would come from either 0 or this thing, depending on which direction this branch went. If the loop never got executed because this Z test failed, I would go down here and get 0. But now that's never possible because if I move this up here, I will always get A times B. So that's going to change the behavior of the program. So, first, so just the first thing to keep the lesson learned. What's the lesson learned here? Loop invariant computation doesn't mean that you can necessarily pull it out of the loop. The fact that it's loop invariant does not necessarily mean you can actually pull it out of the loop. It means that every time we're in the loop, it gives you the same value. Of pulling out of the loop, that's a different story. Okay? So, and if pulling things out can be tricky, you have to be careful. So, what's our solution here? SSA? Oh. So is SSA going to solve, is SSA going to solve everything here? Should we try it?
We could try it.
Let's see. Well, actually, so if we do SSA, what's going to happen?
Your X and Y are going to have different values, so you can treat them because they are loop invariant, and then you're going to have finite to determine which one's going to actually be used, as long as you can somehow handle the exception and return back if you need.
So this X will have a different thing than that X. And we can put that in, and that may have, we may actually get, it'll be okay with this thing, right? So actually that'll solve that problem. Because in fact, X is not incremented inside the loop. So actually we'll get what? We'll get this will be X1, and this will be X2. and actually, and,
The X and the Y would be X too.
what?
Y equals X2 divided by Z.
Right. And somehow, I mean, we have to insert the phi nodes. I'm not actually going to do the whole thing here, but here you need a phi node. You actually need an X3 here, right? Because there's an X1 and an X2 from here. And we can do that, and that will most likely, actually that will, I can tell you, that will fix this problem with this X here. Because it'll basically give a new name to this X right here. But what about the division by 0?
Depends on how you store it.
Well, that actually is very worrisome.
Well, if you have we're talking about C, but if you have a monad instead of the
What? Oh my God,
You
right.
have to make exceptions older than if you have a
I'm not going to get the monads now.
It works.
I explained monads today in 3.5 minutes.
Correctly?
In the lecture, in the earlier, in
Correctly.
What?
Correctly.
I think it was, well, correct. I mean, it was an abstraction of monads. It wasn't quite well detailed. All I can say is people understood monads better after my 3.5 minute explanation than before, which basically means that it achieved something. It was not, it was an improvement. But I'm not, that's not about monads. So, this division by zeros is a big issue because we really don't want to change the behavior of the program in that way. We don't want to add exceptional behavior to the program. That's very bad. So, one of the things that's very draconian is this thing called the domination restriction. So basically, one of the things that you can impose is basically say that if you want to move a statement X out of the loop to the preheader, S has to dominate all loop exits. So what does dominate mean? So in graph theory and in kind of, domination means the following. A dominates B when all paths from the entry of the CSG to B have to pass through A first. So basically you think of this like there's the entry and there's A here and B here. Basically every path to B has to pass through A. There's no way to get to B. But every path to B has to pass through A. That's what A dominates B means. Meaning that if A dominates B, you have to pass through A to get to B. It's almost like A is a gate. It's almost like there's no way to get to B without passing through A.
Okay.
So basically, to move a statement S out of loop, S has to dominate all loop exits, which basically means that so the idea that you can't reach a loop exit without executing S. Okay? Because if you can reach a loop exit without executing S, then you basically could possibly execute the loop without executing S, and then you should not be moving it up, right? So imagine that you have, a loop which goes like this, and then there's a whole bunch of exits, right? So if S is here, right, this is an exit of the loop, this is another exit of the loop, and then here's so if X is here, it dominates all exits, right? Because it dominates this exit, it dominates this exit. If you have to pass through X to reach this exit or this exit. So if X were here, you can move it out of loop, because it would get executed no matter what. But if X were here, then X dominates this loop exit, but it doesn't dominate this loop exit. There's a way to reach this exit this way without passing through S. In other words, this S does not dominate this exit, and therefore, if you move it out of the loop, you're going to force execution of S even though there was a path originally that would go and not execute S.
By that argument, you couldn't remove that.
What?
And how do we remove that?
Yeah, oh, great. So by that argument, we would not be able to remove X in the previous example. Totally. It gets worse. So it gets worse because basically if you look at something like this, which is what a while loop looks like or a for loop looks like, all for loops and all while loops have a check at the beginning for an exit. Right? The first thing they do is they use the check, and if this thing there's a hole, then they exit. So there's an exit right at the very beginning. So there's no chance of any one of these things to dominate all loop exits because it's not going to dominate this one. So basically, what happens is, if you do a normal while loop, you're not going to be able to pull anything out with this domination restriction, ever. Because it may be the case that the while loop does not execute, in which case you can't move things up. Basically, what the domination restriction forces you to only move statements out of a loop if you know for sure that those statements will execute at least once. And in a while loop, you're not guaranteed that any of those statements execute, so you're totally, that's it. Nothing. Nothing. We can't move anything anymore. This is pretty bad. How do we get back to sanity? What? No. Absolutely not.
Convert to do while.
Do while. I don't want to restrict, we can relax the restriction, we'll get to that in a second in some cases, but in some cases you can't. For example, for division, there's no way you can relax the restriction. But there is another kind of loop where if you have a do while loop, then in a do while loop, everything gets executed at least once. Which is great. And then all these statements here, I can pull them, if they are loop invariant, I can pull them out of loop because it would have gotten executed once. So all we need, so basically it's really simple. You remove while loops and for loops, and you force everybody to use do while loops. No, we're not going to do that. Nobody uses do while loops. For some reason, it's always while loops, right, or for loops. Do while are not commonly used. So, okay, do while loops, but do while loops are great for the compiler. For loop invariant code motion, for moving things is great. So what do?
Hi.
We can add an if check.
And then do the do while.
So basically, we can convert a while loop into an if followed by a do while loop. And that's exactly what happens. So what this code will look like is that you first do a check, and then you go out here if that fails. Otherwise, then you go into the do while loop. And now, if you actually insert a preheader here, a loop preheader here, now you can move things out of this loop. And even computations like division, because the domination restriction is going to be is going to hold. Now, you can also circumvent yeah, so you could, but there are ways to restrict this if you actually know for sure, for example, that it's a multiplication. So multiplication maybe is not going to store any exceptions, and you can move it out of the loop. Now the problem is, in that case, you may actually increase the runtime of the program if it turns out that loop does not get executed very frequently, or never gets executed. Then you're going to actually move something out of the loop that will get executed when in fact it's not.
Now that you add in the if do while.
Yeah, but then you're increasing the code size a little bit. Because you insert this additional. Now, in SSA, in some sense, you don't need to worry about, you still need to worry about the, what is it called? The executing instructions that you would not otherwise execute, because you can get exceptions, but you don't have to worry about at least the renaming of things, as we talked before, the things you may clobber, some dependency, etc. So you can move things freely as long as you don't execute something that could cause an exception that you wouldn't have executed before. Yeah.
In most loops, there's scope for constant propagation. If we do that, we don't even need it. If we do constant propagation on n, let's say, if n is a variable.
Where?
If n is a constant, we can convert it to do while anyway, because we'll know how many times the loop could run.
Oh, but n is, let's assume that n is, a lot of times n comes from the user.
Yeah.
Like n is read from the input, let's say. Because a lot of times it depends on on input, on stuff that's read from the disk or things like that.
Okay. But if you could run constant propagation and replace N sum of?
Sure, so if you know that the loop iterates 100 times, like actually in that other example we did, right, I mean, if you know, then you can actually do more clever things. But in general, you may not know how many times the loop iterates. So,
That would actually still be handled, right? I mean,
What?
I'm just thinking if we switched it to the if do while, but we had some kind of constant propagation or even range, like where we have the integer range concept, if we know it's going to run at least once, then that if check will always just be true. And
sure, and you can eliminate it.
We'd get to it.
Yeah, so you can eliminate it.
So, in the concept of not trying to tie so many things,
You can, so sure. So there are ways of basically, so one approach is to always convert all of your loops that way. So you convert all your while loops into do while condition with do while, and in some cases you may be able to remove that condition because some range analysis, some other information allows you to figure it out. Yeah.
What about the while one type thing? You know, while true. Things
Right.
that are meant to like run forever or something.
Right. So in a while true case, what happens then?
you don't even need.
I mean, then you don't even need the if because it's going to be true.
It's true, and I'll just.
Right, so the if true, basically it'll be if true, and then if you do branch pulling on that, it'll just go to the, so that will just convert it directly to clear do without any kind of additional. So if you have an appropriate branch pulling path. Okay, so here's another example. So we have a domination restriction, that's one thing. Now here's another example. What happens here? So what's loop invariant here? What? So this is loop invariant, right? What? That's loop invariant. I mean, that assignment is loop invariant. I mean, this could be like maybe this, I mean, 0 is kind of maybe simple, but this could be like some very complicated, you know, maybe branch pulling will take care of it, but it could be some more complicated loop invariant computation. I mean, 0 is a really simple thing, but let's say it's just a more complicated thing. And you'd like to pull this out. Now here, we can't pull this out.
If you can make it equal, not unless you have like dead cut elimination.
Right, because I mean, if we actually, wait, what happened here?
Z equals 1 is not a live variable.
Yeah, something happened in this example. Huh. Yeah, this thing is dead, right?
Stupid,
Yeah,
yeah.
you remove that and then you can pull it out.
Yeah, then you can pull it out, but if you don't, actually, something's weird with this example. I don't know what happened to it. I was editing this slide, maybe I...
Were you supposed to have a read in between those?
I mean, well, if we actually assume that this is not dead, maybe there's a print here. Maybe there's a print. The point is, we can't move this out of the loop because if we do, we are going to screw up this statement. And we're also going to screw up what this thing, you know, what this thing is actually doing. So, in some sense, if you have something that's loop invariant, you actually have to make sure that, but by the way, this Z here is being used here, right? Because this Z comes from either the 5 or the 0. So if you have a print here, I think the example works out. Basically, now you print Z, this is not dead. So you have to, but the thing is, you can't just pull this out because it's actually, you have to do it every time around the loop because you can't, if you pull it out in normal without SSA, you would actually change the value here. Actually, you would also change the value, you would actually be even worse, you would also change the value here. You basically, yeah, I mean, so, but if you convert this to SSA, everything actually works out. Well, if you don't do SSA, and this is actually why SSA is so cool. Previous to SSA, they have all these restrictions and all these confusing things that you have to think about. So there's a data dependence restriction, where basically, if you want to move S out of the loop, you basically have to make sure it's the only assignment to the Z, and no use of Z in the loop is reached by any definition other than S. So the idea here is that, so you have to have only one assignment to the Z, and if you look at all of the Z's that are being used in a loop, this is the only definition that reaches it, because if there's more than one, then by moving it out of the loop, you risk kind of reordering things, okay? And so it turns out that this is this complicated thing. Getting this right is actually very nasty, but the cool thing is once you do SSA, and you put SSA in here like this, so this is what happens when you put SSA in here. You relabel everything, and now this Z4 is this one right here. And now you're free to move this Z4 wherever you want. I mean, it's just like whatever you want to do with it. You can move it up there, you can move it down here. They're all renamed. So basically what it does is that it allows you to a lot more mobility in moving things around. You still have to worry about executing things that you didn't execute before. And if those things throw exceptions, you should be careful about that. You still have to worry about that. But in terms of data dependencies being broken, SSA completely kind of solves that problem. It just makes it so much easier. Okay. So now, essentially, this assignment here, you can just actually move it anywhere you want. You can even hoist it down into the loop, right? Because this before here.
Because it's been read.
Oh, sorry.
It's only go up.
So yeah, you can't move it down. You still have to make sure that you have the places that are using it. You're basically putting it ahead of the places that are using it. So you can't put it down there, but you can put it up there. So you can move this thing all the way up there, and now you have Z4, the 0, you have Z1 is 5, and yeah. So does that make sense? Okay. Cool. So the reason why SSA, so I think this is for SSA. So the reason why SSA is really cool is because it's very easy to convert to SSA. People have done a lot of different algorithms. If you actually just pick one algorithm off the shelf, it's actually relatively easy to implement. It's very easy to convert back from SSA back to a normal thing. You just insert assignments on the incoming edges of every merge node. And it makes a lot of things easier. It makes code motion a lot easier. It makes CSE easier. We didn't have to worry about reassignment. It just made a lot of things. We didn't have to worry about kind of dependency between statements. It made things a lot easier in terms of code motion and in terms of CSE. Now, SSA was a technique for data dependency. Okay, so we saw how you could use diffuse chains for data dependencies, and then we can do SSA on top of that. Here, the next thing we're going to look at, which is not today because we're running out of time, is control dependencies. How do you encode basically the other side of things, which is control? And the simplest way to do it is using a control flow graph, which is what we've done so far. But there are actually more advanced techniques which are mind-bending and have not gotten a lot of use in practice, in part because they're actually a little bit too mind-bending. But that's what we're going to talk about those next. We had a reading for today. I'm not going to collect them today. I'm going to collect them on Thursday. We're going to talk about that on Thursday. The reading for pointer analysis. I'm going to cancel the reading for Thursday. So we're not going to do.
Cancel it.
Huh? I'm not going to cancel it. No, not cancel class.
No. Cancel or postpone the reading.
I'm going to make it voluntary. If you want to read it, you can read it. If not, then you don't have it. I'm not going to postpone it. What I'm going to do is from next week, I'm going to put up another reading. It's going to be different from that. I figured one pointer analysis thing is enough. And so we'll talk about the pointer analysis thing on Thursday. We're going to do control dependencies on Thursday. And then that's the project. You guys are working on projects? Yes. You should say yes.
Yes.
Okay. All right. See you guys on Thursday.